Cyclic analysis imposes a fully reversed, progressively increasing displacement history at a control node, tracing the structure's hysteretic response, strength and stiffness degradation, pinching, and energy dissipation under repeated load reversal. This window builds that loading protocol, lets you review and adjust it, then inserts the resulting analysis code into the code editor. The protocol can be built two ways, and both end up in the same editable table, so neither locks you out of the other. Generate automatically from a recognized code-based protocol using a number of settings, or add rows manually to the cycle number and displacement table for a fully custom loading history. 4 protocol types are available. FEMA 461 and ATC 24 are standardized, code-based protocols, each with its own amplitude progression and cycle count defined by the standard itself. Constant amplitude repeats the same displacement on every cycle for characterizing degradation at one fixed demand level. Linear ramp grows amplitude in a straight line up to the target. Linear ramp is not a published loading standard. It's provided purely for exploratory analysis and should never be reported as FEMA 461, ATC 24, or any other named protocol. Number of cycles sets the amplitude steps for FEMA 461 and linear ramp, or the cycle count for constant amplitude. ATC 24 ignores this field. Its cycle counts are fixed by the standard itself. Control node and control DOF set where and along which degree of freedom the displacement history is imposed. Maximum displacement is the target amplitude the protocol builds toward or up to for ATC 24. Base reaction nodes takes comma-separated node as integers or tags. The analysis records base reactions based on this input. Inspect members, also comma-separated, adds rich per member recorders feeding the member inspector. Generate protocol builds the amplitude and cycle schedule from these settings and plots it as a loading curve. The resulting table can be edited directly. Add row lets you correct or extend the generated schedule by hand without regenerating from scratch. X-axis, Y-axis, and chart titles can be updated before exporting the chart or including it in a report. Export PNG saves the loading curve as an image. Export Excel saves the amplitude schedule as a spreadsheet. Export PDF generates a full report, protocol type with its governing description and citation, the configuration used, the complete amplitude schedule, the displacement history figure, and protocol-specific assumptions and limitations. Once the protocol looks correct, Insert TCL adds the generated cyclic loading code to the code editor at the cursor position. Run OpenSeas to execute the analysis. The hysteresis curve window post-processes a completed cyclic analysis into its hysteresis loop, its backbone curve, and a set of engineering measures computed from that loop data. It needs a completed cyclic analysis to show anything. It reads and post-processes that recorded response. It doesn't run an analysis itself. The hysteresis graph plots force against displacement, tracing the full closed-loop response through every cycle of the protocol. The loading cycle history plots displacement against analysis step, the imposed protocol itself over time, shown alongside the force response so both can be read together. The window automatically marks the point where a significant strength drop first occurs as an approximate indicator of first fracture or major strength loss. It needs at least 6 local force peaks and 50 data points before it attempts this, and it compares each new peak against the largest peak reached so far, not just an early cycle peak. Phase 1 covers 4 measures. Backbone curve traces the underlying monotonic equivalent capacity, connecting only the first peak reached at each new displacement amplitude, excluding the degraded repeat cycles at that same amplitude. Bilinear idealization fits an elastic post-yield curve to that backbone, giving a yield point and a post-yield stiffness ratio for each branch. Energy dissipation is the area enclosed by each loop, the actual energy the structure dissipates through hysteretic behavior cycle by cycle. Stiffness degradation tracks how stiffness falls off from cycle to cycle, separate from strength, which is covered next in Phase 2. Phase 2 covers 3 measures. Strength degradation tracks how peak force changes cycle to cycle at a given demand level. The window automatically picks the physically correct way to measure this depending on which loading protocol was used, so the comparison stays meaningful either way. Residual displacement is the permanent set left in the structure at the end of each cycle, where force returns to 0 as the cycle closes out. Equivalent viscous damping estimates an equivalent damping ratio from each cycle's dissipated energy using Jacobson's standard formula. Phase 3 covers 4 measures. Auto yield detection identifies the yield point directly from the cyclic response, consistent with the bilinear idealisation in Phase 1. Damage indices computes a Park and Angevin damage index, combining peak displacement and cumulative dissipated energy into a single damage scale, near 0 for undamaged, 1 or above for failure. This one needs the ultimate displacement capacity entered manually, since that's a monotonic property the cyclic data alone can't reveal. Pinching classification measures how narrow the loop gets near 0 displacement, a sign of crack, closure, or slip, and labels the result from no pinching through to severe. Energy history shows dissipated energy per cycle or accumulated across the full loading sequence. A direction toggle flips the sign convention of the plotted data for when a model's displacement or force convention doesn't match the expected orientation. Export PNG saves whichever plot is currently displayed. Export Excel saves the underlying computed data. An export PDF generates a full report covering the hysteresis response and whichever Phase 1, 2, or 3 results have been computed.